All right, the last section of our memory, data, and addressing portion is going to cover a little bit about Boolean algebra, the kinds of things we need to know, the kinds of operators we need to know about to do some bit-level manipulations on these bits we're storing in memory. Let's go through the basics of Boolean algebra really quickly. Boolean algebra was developed by George Boole, that's who is named after, in the 19th century. And basically it's an algebraic representation of logic. We encode true as a 1 and false as a 0. Again, binary number system. And we have a few basic operators. Very important one is the logical AND, often represented with an ampersand as an operator. That says if the variable A and the variable B are true, then the product of their values in Boolean algebra is also true. Okay, so A and B is 1 when both A is 1 and B is 1. Similarly, we have the OR operator, which, as you'd expect, is true if A is 1 or B is 1 or both. And then, of course, we have the exclusive OR operator, often abbreviated as XOR, which is true if A is true or B is true, but not both. So it excludes that case. That's where that X comes from. And then finally, we have a unary operator in Boolean algebra that says the not of A, or the complement of A, is just the opposite value. So if A is 1, then its complement is 0. And vice versa, if A is 0, then its complement is 1. Interesting law in Boolean algebra that can be derived from basic principles is De Morgan's law, which basically says the complement of the OR of two variables is the same as the AND of the complemented variables. And this can be very valuable when we want to eliminate ORs to have only ANDs, or eliminate ANDs to have only ORs in a logic expression. Here are another representation of these basic operators in what are called truth tables. Here we see the operator, in this case the and the possible values of one variable and the possible values of another variable. And this is the and of the two. So when they're both 0, then the and is 0. When they're both 1, the and is 1. And when either one of them is a 0, then the result is also 0. So in the case of AND, it is 1 only when both are true, or 1. For the OR, which we use the vertical bar, you'll see that it's a 1 whenever either one of them is a 1, and only 0 when both are 0. For the exclusive OR, again, if one is a 1, but not both. So in this case, we want to make sure that this is a 0 as well. That's the difference to the OR case that we had here. And then the unary operator, of course, there's only one variable, and it's just the opposite of the value. So that's the basics of Boolean algebra. How we use this to manipulate bits? Well, we can have 2 bytes in memory. Here we're showing 2 bytes, and we can AND them together bitwise, 1 bit at a time. So we can AND 0 and 0, and of course that result would be a 0. 1 and 1, the result would be a 1. In these two, the next cases, these are all 0, the result, except for the last one, where again the 2 values are 1, so we would expect the 1 as a result. Okay, so this would be the resulting AND across these 2 variables. For the OR case, the same values again. As long as one of them is a 1, we'd expect to see a 1 down here. So there's only 2 cases where we would end up with a 0, here and here, where both variable values are 0. Finally, for the exclusive OR, where would we expect to see zeros? Well, certainly here where they're both 0, certainly here where they're both 0s, but also where they're both 1. And that's here at the end, and also right here in the second column. So that result is the corresponding one for XOR. And then for the bitwise complement or not, we would just expect to see the bits flip. Okay? So this is the Boolean operators applied to bit vectors, in this case just a byte's length of bits. And in C we have these exact same operators available to us, and they can apply to any integral data type, long, int, short, or character. Remember character being just a byte. The arguments to these operators up here are treated as bit vectors, and the operations apply bitwise. So you can see here we've declared 3 byte variables, A, B, and C. You'll notice here that we're setting the value of A to the hex 41. That's represented here in its bit notation. And when we take the complement of A and assign it to B, this is the value we get and assign it to B. In hex, this is BE. Not immediately obvious from the 4-1. Okay, but you can see that the 1 and E add up to 16 and the 4 and B add up to 16. All right, if we take the value of 0 and put it in A, as in this case, then the complement is just FF, all ones. Here's a case of an AND. We've taken 69 and 55 as bit vectors, represented here in these values. This should say 69, not 41. And sorry about that error there. This is a 6 and 9. And the bit vector is correct, however. And A and B is just this string of ones and zeros. Again, similar to the example on the previous page, which results in a 41. Okay. So this is how we do bit level operations in C, just using those basic operators. Okay. So the other thing we should know is that 0 is always viewed as false, and anything that is non-zero is true. So the value doesn't have to be 1 to be true. Anything that is not a 0 is interpreted as true. Now, when we're talking about bits, of course, the only values we can have are 0 or 1. But if we apply a logical operator to an entire series of bits, for example, an entire byte at a time or an entire int at a time, then it will only be considered false if that entire int is equal to 0. In other words, all the bits are 0. And anything else, as long as there's any 1 anywhere, then it will be considered as true. All right? This is very useful for early termination of if statements, and we'll see that a little bit later on. But let's take a look at a few examples. Here's the complement. Again, this is now the logical operator, not the bitwise complement, so we're using a different symbol, the exclamation point or bang rather than the tilde. And so the complement of 41 is what we'd expect from our logic is to be 0, false. You notice it's not the bitwise complement. That was a different value. In this case, it's simply 0. If we take the complement of 0, what would we expect to get? Well, actually, anything would do that has at least a 1, 1 in it that would be true. But by convention, we'll just flip 1 bit and make it equivalent to a hex 0, 1. All right, if we AND 69 and 55, as we did on the previous page, we know this result would have been 41 if we had done a bitwise operation. But in this case, this value is interpreted as true. This value is interpreted as true. So our result is simply true, or 1. If we then do 0 AND with 55, a 0 is false. So our result should be false, as it is. Again, let's do an OR operation, and we would see 69 true, or 55 also true, is just going to result in a 1. Okay? So how does this early termination help? Well, for example, suppose that we're looking to increment the value at which P points. P is a pointer to a particular value. And what we're concerned about is that we actually do have a pointer and that our pointer isn't null or all zeros. So we can first say, well, is P true, meaning not 0? So by putting it into a logical AND statement, we can do that test. Here, if P is all zeros, a null pointer, we know that the AND is going to be false in the end, so we can just not do that, not continue evaluating this expression, and it would stop right there. On the other hand, if P is something else other than 0, then we can assume that it's not null, and it's probably a valid address, and we can dereference it, go to the place it points, get the value, and increment it. Okay? So this is a shorthand notation for if P is true, then increment the value at that pointer. All right? But often in C, you'll see this as a quick shorthand instead of having to write that if. And this can be placed in the middle of an expression even to help check that pointer. All right. Lastly, I want to show you how Boolean algebra can be used to represent sets. We'll be using this a few places during the rest of the course. So we can take a bit vector of W bits. Let's say maybe that's just 8 bits for now. What we can do is have each bit represent an element of a set. In this case, the set can have up to 8 elements. And you'll notice in this example here, I have this particular vector, and I can have each bit represent one element of the set. So this bit sequence would represent the set of element 0, element 3, 5, and 6, because those are the ones I've set to 1. Okay? Here's another example, slightly different set, 0, 2, 4, 6. Okay, so you kind of get the hang of how we could represent a set using a bit vector. And now our operators, our bitwise operators, are pretty interesting. The AND can be viewed as set intersection, because it will only be true if the element is in both sets. So if we AND these two bit vectors together, we would get this result, which says that 0 and 6 are elements of the intersection. Okay. Similarly, OR corresponds to set union. If we OR those two values, we would get this bit vector, which represents 0, 2, 3, 4, 5, and 6. You notice that is the union of these two sets, all the elements present. Exclusive OR corresponds to what's called the symmetric difference. In other words, elements that are in one set but not both. In this case, the elements 2, 3, 4, and 5. And a complement is obviously the complementary set. So the complement of the first one, of the second set here, is 1, 3, 5, and 7. All right?